Okay, so in this first example here, where we're describing kinematics, describing motion, doing kinematics in natural coordinates, we have a car traveling in a circular path, right? So this is the path of the car. And then at some, well, let's see, it's increasing its speed. So speed, not velocity, right? So speed as we go around the track, as the car moves around the track, is increased from 15 meters per second to 27 meters per second in 3 seconds. So right in there is, I think, a pretty quick calculation of the acceleration. Let's determine the magnitude of the acceleration when the speed is 20 meters per second, so somewhere in the middle there. Now, at any given time instant, right, we can then, when we're dealing in natural coordinates, right, we want to think about a tangential direction and a right to the center, because we're in a circular motion, a normal direction where these are unit vectors. And what that means is that along the tangential direction is the direction of motion. All right, so this is our velocity vector, which is also always tangent to the path. Okay, so with a uniform speed increase, all right, what we are given, so uniform speed increase, we're given that the change in velocity with time, right, is, so that should say the infinitesimal change in velocity with an infinitesimal time, or a derivative of velocity with time, is a change in velocity with time, a finite change in time, a finite change in velocity due to a finite change in time. Okay, now, and that's given as a, well, the actual difference in velocity is 27 minus 15 meter per second over 3 seconds. So we have a constant dv dt of 4 meter per second squared. Okay, so our acceleration, though, we need to be careful with this. We're asked for the magnitude of acceleration. This is an acceleration, right? This represents an acceleration dv dt, right? This is, this is v dot, right? But in terms of natural coordinates, that is the tangential acceleration. Oh, no vector there. This is the tangential component of acceleration, right? Remember, the acceleration vector is dv dt in the tangential direction, or a sub t, the acceleration. And then we have the normal component of acceleration. That's responsible for keeping the motion in a circular path. Otherwise, if it was only the tangential, right, we would only accelerate in that direction. We would only speed up along the velocity. There's nothing to pull us back in, pull the car back in to keep it in a circular pattern, right? And the force responsible for that, right, is called like the centripetal force, or whatever. Centripetal acceleration, and there's some sort of centripetal force causing that acceleration, but we're not in kinetics yet. We're not dealing with the forces. We're just describing this motion. There must be an acceleration back towards the center at this point to basically go to the next time and curve in back inward, right? We're not curving in towards the center, but curving to keep us in that path, right? So that is along the normal direction, okay? All right, we already said a of t, the tangential component of acceleration, is this v dot, and that is 4 meter per second squared. But our normal component is v squared over r. Okay, so we want to know what the magnitude acceleration is at when the velocity is 20 meter per second, and so we're going to plug in 20 meter per second for velocity, and the radius is always 300 meters. This is a value of 1.333 onward forever, meter per second squared. And so we have our acceleration vector as 4 in the tangential plus 1.33 in the normal at this particular time instant, right? This is because we plugged in 20 there. This is only when we're at the speed 20 meter per second. Or this is the thing that changes. This is always true between the speed of 15 meters per second and 27 meters per second, but this changes, right? This is only specific for this time instant. So our magnitude, to answer the question, is the square root of components squared and then summed, 4/3 squared, which turns out to be 4.2164 meter per second squared. Okay, so this is a good start, and I've got more examples to follow, but that wraps this one up, right? Nice description of motion in these natural coordinates. All right, so in this second example of applying, it's really the theory that we derived for analysis with these natural coordinates, normal and tangential components, normal and tangential unit vectors. Maybe we'll just draw it here on for this system here, right? So what we have here is a perfectly circular motion, a particle in perfectly circular motion. So let's say it has at this time right now an angle theta, but that is a function of time, and it could definitely is going to change. And in fact, the speed at which theta changes is also, or the rate of time at which theta changes is also non-zero, as we will see in our work here. But you can also see as if theta is 2t squared, that means omega, the angular velocity, is also not constant. But but more importantly is what we're focusing on is these way of doing analysis, which is where we actually express in our coordinate system, our reference frame has it kind of moves with the particle, and as it moves, the coordinate system follows it. Right? So instead of I and j, we have this tangential component, which is right in line with velocity. I shouldn't make it. This is definitely parallel to the velocity by definition, and then perfectly normal to it. Right, so it's in the motion and tangential to, and normal to the motion. What we want to find here is with the specified function for what the angle theta is in time. Let's determine the velocity and acceleration of this point P in these natural coordinates, and then how far along this path the distance the particle travels in 1 second, from time 0 to time 1. Noting here that at time 0 our theta is 0. Right, so if we plug in time 0, theta 0, so that means that our, this is our s at time 0, is right there, and then it starts heading off that way. So we want to know basically how far along the circle does it get in 1 second. Okay, so our velocity, we'll start with that, right? Our velocity is the speed at any given time times the tangential unit vector. The speed is r omega for uniform, or for circular motion. This is not uniform circular motion. It's just motion in a circle, not always the same rate. And so we just plug these in. 4 is the radius given in the diagram there. 4t. Oh, we have to do some work here. Omega is d theta dt, which is going to be 2t squared is theta, so 4t is our omega, and that's why that's plugged in there, which equals 16t et, and that's it, right? No, there's nothing else to be done, and that's because we know that the velocity points in the I mean, it's kind of silly even to say. I don't even know which order to say it, right? The velocity is tangential to the motion, and the tangential unit vector aligns itself with velocity because it is tangential to the motion, right? Both of these things, by their definitions, are tangential to the motion, and so, tangential to the path. I should say that carefully, right? These are both tangential to the path. They are along the motion at that instantaneous time. Okay, so this is like where natural coordinates are good, right? Acceleration then has this formula. Okay, where it does have a normal component now, and that's what keeps it pulling. Something is pulling it always back in to stay inside, to stay on the circular path. Otherwise, it was just a tangential acceleration. It would just zoom off, right? If all of a sudden this term disappeared, right, it would just zoom off and never be pulled back in. So this is the thing that's always pulling it back towards the center and keeping it in a circle, right? I mean, we're not actually talking about forces, we're not actually pulling it, but this is the dynamical feature that tells us, the kinematics component that tells us it stays in a circle. If it's just this, nothing's going to keep it in a circle. Okay, so alpha, which is this omega dot here, or theta double dot, right? We just come up here, take one more time derivative. That's just 4. That is a constant, so we're constantly accelerating as we go along. And I think that's it. Now we have everything, right? So our A acceleration vector is going to be 4 for the radius, 4 for omega dot. So we're going to have 16 there for our tangential component. And for our normal component, 4 for the radius, 4t is omega. We'll square that, e sub n, normal unit vector. So simplifying, we get 16 e hat t plus 64 t squared e hat n. And that's it for part A. Okay, not too bad. All right, if we're specifying the angle as a function of time, these type of analysis is very, very straightforward, right? Even though it's kind of hard to think about the coordinate system shifting, and there's a lot of the description is in the fact that we used tangential and normal components, right? It tells us like this is that acceleration that's keeping us in the circle, right? The second part is how far have we traveled in the 1 second? Well, there we just are really just calculating an arc length, right? This is maybe if I can sneak it in here, right? Since theta is a function of time, s is a function of time, right? And what that really is this is the arc length from theta equals 0 to theta at some time later on along the circular path. Okay. So our change in our s coordinate, change in position, is going to be the s at t equals 1 minus s at t equals 0, which will just go to so we're going to plug in r theta at these different times. So r in both cases is 4. Theta is 2t squared, right? 2t squared, where we're doing r times theta for these two instances. This is our change in position. It's really the arc length. But it's kind of silly to even have this term. We just know this is going to be 0, right? Because of this, because we start theta, we start s right here at s equals 0 because theta is defined. 2 times 1 squared minus 0, so 8 meters, right? 8 meters. 8 meters, that is twice our radius, right? So that means that we've gone two radians. 2 radians, pi over 2, no, I'm sorry, pi is 3 radians, so we actually only make it to somewhere about here in 1 second, right? The particle moves from here to there in about 1 second, based on that definition. Okay, that's it for this one. All right, so example 3 now here gets a little bit, a little bit more involved, not just circular motion. All right, so we have an electric car traveling along like a racing track here. The racing track has 2 of these straight segments at 200 meters apiece, and then 2 semicircular sections at the 2 ends here with the radius 50 meters. And we're going to put the electric car here at A at time 0 and specify the acceleration of the tangential component. So this is going to be the acceleration along the path throughout the entire track, through the entire progression of the car from A to B. And from this specification, we want to determine the velocity and the acceleration at point B. So, we know the velocity. Well, let's go to an arbitrary point like here, right? We know the velocity at anywhere here on this stretch is just going to be right along that stretch. And we're specifying, the acceleration along that direction perfectly. And the velocity here, right, is going to be tangent, and maybe somewhere along the way would be tangent as well. But the acceleration along here is not just the tangential component alone. Okay, and so that's going to be part of determining the velocity here, or determining the acceleration at b. We're going to need to know the normal component of acceleration, which is not 0, as we can see. Okay, but let's draw the unit vectors on here just to remind us, right? This one's nice because it has a semicircular, it's a circular nature to it, right? There is your, anywhere along here, this is your tangential unit vector, and there is our normal unit vector, right? So always good to keep those in mind. Okay, let's get going here. Okay, our acceleration, the tangential acceleration, this is no matter what. This is true for both the straight line portion, which is rectilinear, or curvilinear motion. This is always true, that the tangential acceleration is always dv dt. It's just if it's a straight line, that's all there is, right? There's no acceleration anywhere else. Okay, so then we do the trick here where, yeah, we're just going to flip this around, dv dt, and then plug in and give ourselves some space there what a of t is, because that's specified, which is 1 plus 0.2t. And to this, we then integrate in time up to some arbitrary time. Okay, and the reason we do that, by the way, so this over here is dv. This is going to turn into an integral in the velocity variable. The reason we do this, right, is because we have a specified acceleration in terms of time. Okay, so then this one here, we're going to integrate from 0 to v, right? We start at rest. I don't think I said that, right? It starts at rest. Starting at rest at a, at time 0, right? That's okay, and then we're starting at rest and going up to some velocity v of dv, and then we can actually do the integral here on the right hand side, which is t plus 0.2 t squared over 2, 0 to t, and well, this is just now v of t. This is our velocity. This is now the velocity in this straight portion, right? Velocity of t is going to be t plus 0.1 t squared. Okay, good step, not what we need, right? But it's going to get us in the right direction, because what we need to know is this is by the way, this is our velocity always in the speed, I should say, right? It's not actually the velocity. This is the speed, and speed always. This is true for both the straight line and the curvilinear portion, right? So you could say, well, this is the velocity. Well, it does give us a long way in terms of the velocity, but we do need to be careful with this. Okay, so to move on, this is defined to be ds dt. Okay, we then take this relationship here, flip it around and integrate. So we'll be integrating from 0 up to some s location ds, integrating this in time, t plus 0.1 t squared dt, right? So that one more integration will give us the position as a function of time, which is going to be t squared over 2 plus t, that's a squared, over 2 plus 0.1 over 3t cubed. We should also say, by imposing that little thing right there, that 0 there, what we're saying is the choice for our coordinate s, maybe back to the picture, is right here is our s equals 0 point, right? A bit of a choice. Convenient choice, wouldn't just make life harder to do anything else. Okay, what we have here is the total distance traveled. Total distance traveled from the initial time to, so t equals 0, to time t. Okay, and this again is valid for both the straight line portion and the curvilinear portion, all stemming out of the fact that this is true, right? That the speed is the tangential component of acceleration for both definitions. Okay, so then the question we have to answer is how far is it from A to B, right? See where we're going here, right? Well, then we can detail how far the position is, right? Okay, so that's going to be smart. So the value of S when we get to B is going to be the 200 meters traveled on the straight portion plus a half of a semicircle. Half of a semicircle, right? Well, this is going to be an arc length. Anytime we have an arc length, right, is going to be arc length of a circle is going to be the radius times the change in angle to get to B. Let's go back to our original diagram. All right, so we have here is to go from there to there. There's your change in angle, B. Or having said it, right, we're going from nothing up to here, right? So we're going from no angle, or perfectly horizontal, to vertical, right? That's maybe even the better way to see it. Regardless, some way we can convince ourselves that this is a quarter of a circle, so pi over 2, 90 degrees. All right, so we have 200 plus 50 times pi over 2, which is 278.54 meters. Okay, so that's helpful. We know the S value once we get to B. So then we could ask, well, now that we know that, what is the time? At what time does car reach B? Okay. Now here this gets a little bit tricky, right? So here we're just we want to find the time, the critical time when our S value has reached SB. Okay, and the reason we need this is because we need to know the velocity at that time, right? So we're determining what the time is to back our way. Okay, so we need to solve t squared over 2 plus 0.1 over 3 t cubed, which equals 278.54. Okay, this requires some sort of a cubic solving. This could be done graphically. You could do this in Wolfram Alpha. You could do this on a lot of calculators. I think I went onto Desmos.com, plotted this out, and you write a little function here, and looked where it crossed 0. The function would actually be t squared over 2 plus 0.1 over 3 t cubed minus 278.54, and look where that function crossed 0. Or you could just plug this into Wolfram Alpha, right? Regardless, we get that the important time here is 16.3311 seconds. And this is a critical time, so maybe we, what can we do here? This is the t sub b. How about that? Since we're setting it equal to s of b, this is t sub b, right? Okay, great. So now the next step is what we have, the questions were, what we're trying to answer, what are the velocity and acceleration at b? We have the velocity anywhere, right, throughout the entire motion. We just need to evaluate our velocity at that time to get to what the velocity is at b. All right, so let's do that. Velocity at b is going to be the velocity at time t equals tb, which is going to be, let's see, what's the velocity is t, so that's 16.3311 plus 0.1 and then t squared, so 16.3311 squared, and we get almost exactly 43. Okay, so our velocity vector at b is, so maybe we subscript that with b as well, is going to be 43 in the tangential direction meter per second. Which, by the way, well, so that's the answer because that's in the natural coordinates. Note here that this is actually 43 meter per second j hat, because b at b, the velocity, the tangential unit vector is perfectly up, right? In the j hat direction. If we were asked to also do this for the Cartesian. Okay. Now, actually, let's do this. Let's ask if we can show this in a different way, as just a little bit of an exercise. Why, just mathematically, not from the diagram or just from our intuition. Why is this true? Well, remember, so theta b is 90 degrees, right? We went from no angle to now a right angle. Theta b is 90 degrees there, right? So, this is just a little side note, by the way. Theta b is 90 degrees. At 90 degrees, cosine is 0, sine is 1. So at b, the tangential unit vector is cosine, right? So this is back to our transition. How do we convert from I hat, j hat to our nt coordinate system, right? So this is going to be cosine, let's just write it out, cosine theta b plus sine theta b. Well, this one is nothing, this is just 1, so this is just j hat, right? Well, and if e of t is j hat, we know that e of n must be I hat, or at least related to it. So let's work through the relationships there, right? E hat n, we showed last time how this was minus sine of theta I hat plus cosine of j hat. This is 0, this one equals -1, and so we get minus I hat. And does that make sense, right? Once we get to b, the normal is in the direction of motion, which is the velocity, and n points towards the center of curvature there, right? Which is in the negative I hat direction. So we're going to compare what I and j are, right? Ooh, my pen's going a little bit dry there. I hat j. So en at that point would point in the negative I hat direction. Okay, good check. All right, so let's finish the problem now. Finish off this video. Let's see. Little thought bubble there. Okay, so now we need to get the acceleration vector, and that's all that's left. Okay, acceleration vector is the tangential component plus the normal component, where a of t we know, that is 1, I mean this was specified in the problem, 1 plus 0.2 times t, so we're plugging in the time to reach when we reach b, 4.2662 meter per second squared. That's our tangential component of acceleration, and our normal component at t, actually let's write it out for general t here for a second. That's just v squared over r. And now at the time we reach b, that's going to be 43 squared over 50, which is 36.98 meter per second squared. Great, so our acceleration is going to be 4.2662 e hat t plus 36.98 e hat n with the units of meter per second squared. And that would be it, but we could also, just as an extra note, say, well, we also know this is going to be 4.2662 j hat. Careful, the tangential component is j hat here, and then the normal component is minus I hat, so minus 36.98 I hat, again, meter per second squared. Okay. All right, so that's it. So The next step is going to be moving into polar coordinates, but this sort of wraps up our examples here for tangential and normal components, or what I call the natural coordinate system.